Okay. Hello everyone. In this video, I will present 10 problems of organometallics from Csir Net Pyqs. So let's begin. So the first problem is for the typical Fisher and Strock carbons, consider the following statements. Statement 1 is oxidation state of metal is low in Fisher carbon and oxidation state is high in Strock carbon. Statement 2 is auxiliary ligands are pi acceptor in Fisher carbon and non-pi acceptor in Strock carbon. Statement 3 is substituents on the carbon-carbon are non-pi donor in Fisher carbon and pi donor in Strock carbon. And carbon-carbon is electrophilic in Fisher carbon and nucleophilic in Strock carbon. So you need to choose the correct statements between A, B, C, and D. So let's begin with the structure of a Fisher carbon and Strock carbon. This is Fisher carbon. Here you see this carbon-carbon is attached with the heteroatom, that is oxygen here. But in case of Strock carbon, it is here carbon-carbon is not attached with any heteroatom. And next is in Fisher carbon, in Fisher carbon metal is electron rich and it is in the low oxidation state. But in Strock carbon, metal is low electron deficient, so it is in the high oxidation state. In Fisher carbon, auxiliary ligands such as carbon monoxide is present here, say. So it is a pi acceptor type of ligand, and in the Fisher carbon, see the substituent is OMe, which is acting as a pi donor ligand. But in the Strock carbon, there is no such type of auxiliary ligand which is pi acceptor. So here you see the statement 1 is correct because here they say oxidation state of metal is low in Fisher carbon and high in the Strock carbon. So statement 2 is also correct, that is auxiliary ligands are pi acceptor and it is non-pi acceptor in the Strock carbon. But if you see the statement 3, they are saying substituents on the carbon-carbon are non-pi donor in Fisher carbon. But here you see the carbon substituents on the carbon-carbon, it is pi donor in the Fisher carbon. So we can eliminate this third option. The next statement is carbon-carbon is electrophilic in the Fisher carbon. Yes, it is correct because in Fisher carbon, carbon-carbon is electron deficient, so it is acting as an electrophilic in nature. And in the Strock carbon, carbon-carbon is electron rich, so it is acting as a nucleophilic in nature. Okay. So the correct statements are 1, 2, and 4. So the option B is correct. Okay. So let's. So the next problem is the binding modes of nitrosyl is in the 18 electron compounds CO, CO3, NO, and nickel pentaheptacyclopentadiene nitrosyl respectively. These options you need to choose this option. What is the correct options? Okay. So in the binding modes, it depends on how many electron donor, that is nitrosyl, is with the metal. That is, if the nitrosyl donate 3 electron to the metal, then it acting as a then it will bind to the metal in the linear geometry. If it is donate 1 electron to the metal, then it will then its binding mode is bent geometry. Metal nitrosyls are linear. If it will act as a 3 electron donor, those act as a 1 electron donor, then it will be bent in geometry. See the first complex. In the first complex, first we will see the electron count, total electron count. See total electron count for carbonyl, it is counts as 9. No, for cobalt it is 9, and for carbonyl each contribution is 2. So 2 into 3 plus 3. So it will total is 18. See here, nitrosyl is acting as a 3 electron donor. So here binding mode is the linear. Next is this one, nickel complex, nickel's pentaheptane nitrosyl complex. Uh, in this case also we will calculate the total electron count. Here you see the total electron count. For nickel it is 10. For pentahepta cyclopentadiene contribution is 5 plus 3. That is from the nitrosyl. So total will be 18 electrons. So it is so here also you can see the 3 nitrosyl acting as a 3 electron donor. So the binding mode is nitrosyl binding mode is linear. So the option here, correct option is option C. So next problem is among the following, they are giving the four complex. You need to give what is the compounds with most shielded and deshielded Cp protons respectively are. Uh, Here you see the first complex. Here Cp rings. This is the Cp rings. In the above Cp rings, due to the presence of this pi acceptor CO ligands, carbonyl ligands, it will make the it will make this metal electron deficient. So and this electron deficient metal will suck the electron density from the cyclopentadiene ring. So it makes this Cp protons as deshielded much more than others. Okay. Next is so it is so Cp in this complex, Cp protons are much more deshielded as compared to others. And in this complex, that is ferrocene, here the Cp protons are shielded due to the small size of iron, that it is more close to the nucleus as compared to the ruthenium complex and osmium complex. So Cp protons are much more shielded in case of ferrocene. So the option one is correct. Here D is the ferrocene is much more shielded Cp protons, and option A is has the much more deshielded Cp protons. So option A one is correct option. Okay. Next question is total number of vertices in the metal clusters is 6, 5, and 5 respectively. The predicted structure of these complexes respectively are. So here you need to find out what is the metal structure, that is like closo, nido, arachno, and etc. Okay. So let's see. We will apply the 14N rule. First here we'll first let's see the first complex, first metal cluster. Here we will calculate the total electron rule, that is total valence electron. Here you see 6 for there is 6 ruthenium. So from ruthenium, total number of electrons it is comes, total valence electron is 8. So 6 into 8 plus, for carbon it is 4. For carbonyl, for each carbonyl it is 2. So 2 into 17. So total is 86. Now which is equal to 14 into 6. That is 14 into metal. Total number of metals is 6. 14 into 6 plus 2. So it is 4n plus 2 type of complex. So it has a closure type of structure. In the next structure, osmium 5, carbon, CO 15. In this case also we will calculate the total valence electron for each osmium. Total electron count is 18. So 8 into 8 into 5 plus for carbon it is 4, for carbonyl it is 2. So 2 into total number of carbonyl is 15, so 2 into 15, then which is equal to 74, which is equal to 14 into total number of metals, that is osmium 5. So 14 into 5 plus 4. So it is 14N plus 4 rule. So it is, so its structure is like a nido type of structure. Next complex is ruthenium 5 carbonyl 16. So same way we will do. We will first calculate the total valence electron. In case of ruthenium, same total valence electron is 8. So 8 into total number of ruthenium is 5 plus in case of carbon, valence electron is 4. In case of carbonyl, contribution is 2. So 2 into 16. Total number of carbonyl is 16. So which is equal to total valence electrons is 76. So which is equal to 14 into total number of metals is 5 plus 6. That is, it is 14N plus 6 rule. So it is a arachno type of structure. So what is the correct option here? See, in the B option, it is given as closo, nido, and arachno. So our correct option is option B. Okay. Our next question is with respect to the sigma and pi bonding in platinum alkyne complex in the structure given below, which of the following represent the correct bonding? So in this platinum alkyne complex, see, platinum will here alkyne will acting as a sigma donor and pi acceptor. And so here you see the first option here, M sigma electron which is in the first option you see M sigma, it is M sigma to L sigma. So it is not correct because electrons is coming from L sigma to M sigma, that is ligand that is alkyne to metal. So option, we can eliminate this option because it is not correct. Option 2 is L sigma to M pi. Yeah, it may be correct, but in the next option you see it need to be aimed here L pi to M pi. Here ligand pi electrons here pi back donation from the metal to ligand, but it is opposite. Just they are saying that is ligand pi to metal pi. But in the fourth option, if you see here, ligand pi orbital, it will donate its sigma electron to the metal, and in case of a metal, it is also acting as a pi back donation to the metal, to the ligand, that is alkyne. So it will be so back donation is from metal pi orbital to the ligand pi star antibonding orbital. So option number 4 is the correct option. Okay. So the next question is for the reaction of ferrocene eta 5 C5H5 CH3 CO2 with PMe3, the main intermediate, we need to find the intermediate of this reaction. So let's see. In this reaction, see this complex 18 electron. This is the 18 electron complex. So so this one is stable complex. So for reacting this complex, make it reactive, we make it to 16 electron or less than 18 electron complex. So first it is undergoing the 1,2 micrometer insertion. So no, it is 1,1 migrated insertion. There is something wrong. Okay, so it gives the 16 electron complex. Then it is as the intermediate. Then if we react with the trimethyl phosphine, it gives this 18 electron complex. So our intermediate is the 16 electron complex, which is similar to the option number 2. So option 2 is the correct option. Next problem is the intermediate and the final product of photolysis of from the following. You need to find out the intermediate and the final product of the photolysis of this complex. Okay, so let's see. Here, this is a 18 electron complex. Under the photolysis, that is photochemical condition, it will undergoes the decarbonylation. So after the decarbonylation, it will be in the 16 electron complex. Okay, then after this, this allyl ligand will convert it into the eta 3 configuration, eta 3 hapticity. That is, here the hapticity is eta 1 and here the hapticity is eta 3. So it converted into the 18 electron complex. So the intermediate is same like option B, and the final product is same like as option D. So the option number 2 is the correct option. Okay. Next problem is the major product of the major products A and B in the following reaction sequences are they are given the Graf's catalyst and the alkenes. Okay, so let's see. This is an example of the ring closure olefin metathesis reaction. So this is the reaction. In this reaction, you see the graphs in case of Graf's catalyst. This one is Graf's catalyst. Ruthenium. This is a type of Strock carbene. This here it forms like a cyclobutane type of structure. See, when this alkene double bond is attack here, this double bond attack here, so it forms a cyclobutane that type of structure. After the elimination of this CH2 and double bond CH-PH, it will form this another carbene, that is ruthenium. This is a type of Strock carbene, and again it will undergo this again undergo this ring closures type of reaction. It will form this type of cyclobutane type of structure. Then it undergo bond cleavage to remove this ruthenium carbene, that is ruthenium double bond CH2, and it gives us some amide. This is the intermediate. That is A, option A. Then it undergoes the reduction with the lithium aluminum hydride. It converted into the amine. Okay. So here you see the option 3. Here option 3 is the amide is the option A. Option that is the this A is this amide and the B is this amine. So option 3 is the correct option. Next next question is the reaction of this complex manganese carbonyl complex with iodine results in A without loss of carbonyl, and compound A on heating to 120 degrees Celsius loses a carbonyl ligand to give B, which does not have a manganese bond. Okay, so the compound B reacts with the pyridine to give two equivalents of C, A, B, C, A, B, and C from the following. You need to choose this. Choose A, B, C. That what is formed from this uh, from this structures, from this given below structure. Okay, let's see. Here you see the manganese carbonyl complex. It's like a 18 electron complex. So here you see the 2 carbonyl, it is in the bridge position, and another 4 carbonyl attached to the manganese is with the terminal is called as the terminal carbonyl. So when it reacts with the iodine, it will not undergo any no, without any loss of the carbonyl. So it is remain as the 18 electron complex. So under the heat, it will undergo decarbonylation to give a 16 electron complex like a dimer type of structure. And and after the reaction with the pyridine, it gives again 18 electron structure because 2 electron will be contributed in this complex, so it gives 18 electron type of structure. So this one A, B, and C. So here you see the option 1 is the correct because here you see the structure 2 is equivalent to A, so 2 is A. Then 5 is equivalent to B, C 5 B, and 4 is equivalent to C. So option 1 is the correct option. And the last problem is you need to find out the major product formed in the following reaction. This is a type of intramolecular Heck reaction. Okay. Mm, Here in this reaction, first it undergoes the oxidative addition. Here they are given this palladium catalyst. So it first it undergoes oxidative addition. So what will be, and this carbon and halide bond will be broken, and it undergoes the oxidative addition with this palladium ligand, palladium catalyst. So it will be here iodine. Mm, Palladium is bonded with iodine, that is halide, and this whole carbon chain, that is your whole carbon chain. Then it undergoes the iodide elimination. So this double bond will undergo eta two, and this double bond will undergo eta two bonding with this palladium ligand. So so it gives this type of palladium eta two structure, palladium eta two bond with this alkene. Then it undergo this 1,2 migrator insertion. When it undergo 1,2 migrator insertion, that is this bond will bonded with here, will come here, and will this double bond will come here, come to the palladium. So it will bonded as PDLN, this bond, and then cyclohexane. Then it will form this uh, cyclopentane type of structure because if you count the if you count from here, see here the 5 membered carbon is 5-membered ring will be formed. That is 1, 2, 3, 4, 5. Okay, so 5-membered ring will be formed. After the beta hydride elimination, here see beta hydride elimination, it will form this type of structure, which is it is a reaction with a Sin's stereochemistry. So this product is formed as the major product. So the option 2 is the correct option. So thank you for your patience. If you have any doubt, then put it on the comment section.